Thank you for having me. Thank you for the time. My name is Dave Yarmosh. I'm a bioinformatician with ATCC, and I hope you enjoy a little bit more crunch to go with all of these big applications. Over the past day or so, we've heard a lot about how Oxford Nanopore data can be used for your purposes, but each of these has their own set of needs, right? And so these needs ultimately ask the question of how good is good enough with your base calling, because that's where a lot of this begins. So first things first, ATCC, you may have heard of us, is the oldest and most expansive biorepository in the world. Our collection is absolutely enormous, and this year we began the launch of the ATCC Genome Portal. As of now, the Genome Portal has roughly 5,000 microbes, or it's about to approach 5,000 microbial genomes, and these are intended to demonstrate the genomic qualities of all of our microbial products. But part of that is reproducibility, because ATCC is also a standards organization. So when Oxford Nanopore launched the Dorado software, we couldn't simply adopt it, right? Taking changes into our production processes is a complicated and heavily justified procedure. So we set out to evaluate that in more detail. Oh, I got one over here. So part of the Genome Portal has required the Oxford Nanopore sequencing technology. The long reads have been absolutely essential in the bacterial and the mycological collections, and steadily more so in the virology collections as well. Now, until recently, the base calling has by default been performed with Oxford Nanopore manufacturing specifications, which is to say the high accuracy base calling mode. Dorado introduced us to an opportunity to consider the other options that are available to us. And so because we're performing about 1,000 publishable microbial assemblies per year, we needed to consider that we can't simply sacrifice accuracy for speed, nor can we simply sacrifice speed for accuracy. There's a balance that we need to meet, and I imagine that we're not the only ones in this room that have that concern. Excuse me. Further, like I said, our collection is enormous. We have to consider the possibility that the softwares work and perform differently across different microbial taxa. And so these hybrid Illumina and Oxford Nanopore assemblies that we've been performing, hopefully we'll see an improvement as we progress into Dorado. Effectively, what we're talking about is a benchmarking study, right? So, like I said, we need to balance the throughput demand. We need to account for the possibility that different organisms behave differently. And to touch on that a little bit further, the base calling software that we use, whether it's Guppy or Dorado, these are based on AI machine learning models. That means they had a training set, that means they had a test set, and at least I personally don't know what was in either of those. So the possibility that different genomic content, be that GC content, tandem repeat regions, secondary structures, any of those may have an impact on the Oxford Nanopore ability to base call, is something that I'm not personally keenly aware of. So we need to be concerned with the breadth of our collection. And like I said about the difficulty of performing an upgrade, we need to just see if changing software is easy, right? Sometimes anyone who's tried to install something from GitHub, you may find sometimes it's a simple install, sometimes it takes you 3 hours. So that's what we're going to look at, and we're going to start by doing some simple statistical analysis, and that is to say talking about read quality scores, lengths, base calling speeds, but we're going to take it to the next step and talk about the assemblies as well. And we're still going to keep it high level. It's going to be just assembly lengths, contig counts, N50s, that kind of thing. And obviously these are admittedly very high level and in some ways superficial statistics, but we think these are some of the most universal needs across all sorts of labs. Not everyone needs to go all that much deeper, but these basics will get you where you kind of need to go. And like I said, we have an enormous collection. We took our enormous collection. We had our entire data set that was, at that point, by abstract submission, sequenced on the R10 Flow Cell, comprising 8 viruses, 36 fungi, and 239 bacteria. And we hoped that the sheer size of this was going to outweigh the possibility that different genomic constraints were going to impact the base calling. From here, we had sequenced them. We rebase called them 6 different times. That is 3 times on Guppy and 3 times on Dorado in the fast accuracy mode, the high accuracy mode, and the superior accuracy mode. So we can compare these neck and neck, because we're not just talking about upgrading from Guppy to Dorado, we're also talking about proving it's an upgrade. From here, we took their base calling, and then we assembled them with Fly. We did a couple other assemblies, hybrid assemblies, other tools. We're not going to be talking about that today, just for the sake of time. I'm already halfway through my time limit. And we're going to look at the N50s. Now, other sources of variability exist, and especially in public data sets where not everything is completely traceable. We chose all of our samples that were sequenced by the same user on the same instrument. They were base called on the same hardware. Even the library preparation was as identical as possible given the natural constraints of different organisms, gram-negative, gram-positive bacteria, for instance. So with all that included, we ended up with, I'm going to hesitate on the number here, 1,698 total assemblies, and I believe today I'll be just talking about the bacterial collection, which is 1,434 assemblies, which, like I said, I think makes this the largest base-calling benchmarking data set to date. Plenty of people have spoken about the quality scores and how they may change from the fast accuracies through the superior accuracy mode, the read lengths and all of that. I'm not going to talk about that because they're correct. We've seen it. The superior accuracy mode is indeed more accurate, but instead I just want to talk about speed. Simple, straightforward, and to begin with, I want to focus on what I think is probably the weirdest thing that I see on this chart. Dorado in the fast mode and Dorado in the hack mode operate in the exact same millions of samples per second across our entire data set. This is all three collections. That was something unexpected because Dorado is intended to be a faster version of Guppy, not necessarily more accurate, at least not directly, but faster. And in these two modes, you can see they're exactly the same. That's not a quirk of the data or a quirk of the scale. They are perfectly identical. By contrast, if you look at Guppy versus Dorado, Guppy is 2 to 3 times the speed of Dorado when run in the fast mode, completely subverting my expectations and what Oxford Nanopore has said. But don't worry, they're not lying to us. Dorado is faster. The moment you get into the high accuracy mode and the superior accuracy mode, you can see now that Dorado has a 2 to 3-fold enhancement over Guppy, right? So taking for granted that the accuracy modes are labeled correctly, there is no reason for starters to use Dorado in the fast mode when the high accuracy mode is available to you, and it will be available to you. And if you really are pressed for speed, you might want to fall back to Guppy. Before I leave this slide, I do want to focus, just draw your attention quickly to Dorado in the superior accuracy mode versus Guppy in the high accuracy mode are almost exactly the same speeds. For all intents and purposes, they base call at the same rate. So if you were previously using Guppy with just your default settings and you've upgraded to Dorado, you can achieve the same exact throughput you did before, but now with a higher degree of accuracy. And so when I say Dorado isn't more accurate than Guppy, it's not, but it does allow you to be more accurate than Guppy did. And so that is essentially worthwhile. And real quickly, it does seem interesting that, in my opinion anyway, as you increase the accuracy, the effect of the different collections seems to wane a little bit. Now, we've got a smaller sample size for everything that isn't bacteria, so remains to be seen as we continue to sequence. But I just wanted to highlight that because sooner or later that may become very interesting. Okay, so on to the assemblies. The x-axis hasn't changed. The y-axis now is doubled. We've got the assembled bases in terms of the assemblies, overall base count, and then the N50 in the darker blue. And on the right, we've got contig count that's represented by the line graph. Once again, I want to look at Dorado as this kind of anomalous section in the terms of the fast mode, because you can see from Guppy in the fast mode all the way to the right that all of these values are relatively consistent. Right? I know the line graph for the contig count is all up and down, but it's changing by about 3 contigs across the entirety of it. But these assemblies from Guppy fast and over are all within 1 or 2% of each other for both the overall assembly as well as the N50. And Dorado in the fast mode is not so much. It is substantially smaller by comparison. So if you thought that on the last slide that Dorado and Guppy were actually, or Dorado in the fast and hack mode were the same, rest assured they weren't. What I do want to look at real quickly before I run out of time, which I'm rapidly doing, the contig count drops here. Usually between Dorado and Guppy, the contig count drops. But what's worth noting is the N50 stays very static. And without going into the details of how that's calculated, that does imply to us that all the contig differences between Dorado and Guppy, between the fast and the superior accuracy modes, are negligible. These are short contigs that are not providing very much information to the overall assembly. So maybe Guppy looks on paper as though it's a little bit better. This is about 1 contig difference, but in practice, you're not going to see that dramatic of an effect. Hope you don't mind I go over and steal a little bit from the questions, but what you really need to think about is how good is good enough? What is your use case? So maybe you're doing field-forward sequencing where you just need some basic taxonomic identification, and speed is your answer because you want it in real time. Guppy in your fast mode is going to give you that. If you've got some difficulty altering your settings, altering your tool, sticking with Guppy is not going to give you a significant accuracy drop. It's okay, it's probably acceptable. If you can alter your settings, switching to Dorado and the superior accuracy mode in most cases is going to be your best bet, because at a rate of 1 GridION run, say 4 flow cells, 8 samples a pop per week, Dorado in its superior accuracy mode achieves the same uptime that Guppy did in its high accuracy mode, which is to say 100% uptime. We can talk more about these details later. It's flashing red at me. But I do want to say that we set out to optimize our use of the GridION, set out to find the evidence that we can make this change. We did just that. We're satisfied with the change from high accuracy to superior accuracy, Guppy to Dorado. More work is coming to show off the virology and the mycology collections, and last but not least, the most significant reason, as we've all heard several times so far, to use Dorado is the enhanced and ever-increasing methylation models that are available to it that are not being supported on Guppy the same way. And with that, I'd just like to thank my team. This is the ATCC Sequencing and Bioinformatics Center, and Karina Tabrin is the biologist that has performed all the sequencing. She's around here somewhere, so give her a shout if you see her. She's very impressive with the 2,000 plus data sets she's created for us. Thank you very much.